Hello everyone. Today we are going to discuss to solve traveling salesperson's problem using dynamic programming. So we have seen traveling salesperson's problem, solving traveling salesperson's problem or TSP problem in short by branch and bound method. Today we are going to see how it can be solved by dynamic programming. So TSP is a classic optimization problem, and the problem statement is that the salesperson will visit all the cities. So they will be given cities, and salesperson will visit all the cities exactly once except the starting city. So it is a classic optimization problem where a salesperson must visit each city exactly once, return to the starting city, and minimize the total travel distance or cost. So we'll consider the travel distance. That means let's say city A to B, whatever the distance is, that distance we will consider as a weight or travel distance. So overall, when the salesperson will come to the original city or the starting city, the total cost should be minimum. So this is called traveling salesperson's problem. So, so the problem statement is given a list of cities. The distance or the cost between each pair of cities will be given, and we have to find the shortest route or shortest route that visits each city once and returns to the start. That means the catch is that each city has to be visited exactly once, not more than one. Whereas in Wildlife tour or in case of Wildlife tour also, you can visit each city more than one time. But in case of TSP, that is the catch line. Each city must be visited exactly once, except the starting city. So starting city always the salesperson will comes back, and by this process, what will be the minimum cost he should be traveling? So that is the intention. So it's a minimization problem. So one simple example could be that here you can see that these are the cities. So 0, 1, 2, 3, 4 cities are there, and in between pair of cities, you have distances. So this is distance cities 0 to 1 is 10, 1 to 2 is 25, 2 to 3 is 35, and then 3 to 0 is 20. So these are the distances you can imagine. So each city has a distance. The goal is to find the path like 0 to 1, 1 to 2, 2 to 3, and 3 to 0. So salesperson has again come back to the starting city which is 0. So by this process, the total traveling distance should be minimum. However, you have to remember that TSP is a NP hard problem. That means it cannot be solved in polynomial time. That we have discussed when we discussed the NP completeness. Saw that approximation algorithm that TSP is the NP hard problem. That means it is solution is not possible in polynomial time. In fact, today that we are going to see the dynamic programming, the dynamic programming is just a mere solution itself. It is not an optimal solution. Time complexity in that case also it will be exponential. So usually the TSP problem can be solved by brute force, dynamic programming, heuristic, or approximation. So you can see here the cities and the distance between the each cities given here. So these are the cities A, B, C, D. So this is you can see that both way the arrow is there. That means A to B and then B again B to A. So this is how you have shown it here. So the connection is there from A to B. That means salespersons can visit A to B or you can come back from B to A. Similarly, from other cities and all connectivity has been shown and the corresponding weight matrix has been given. That means the distance between all pair of cities that is also given. So all cities, city A to A, city B to B, all distances are 0. Remaining all distances have been given here. So one thing has to be noted that city A to B can be let's say 2 kilometers, while city B to A can be 7 kilometers. So the distance from city A to B while traveling can be lesser than when coming back from city B to A. So these cities are, the distances are varying actually. So what could be the probable solution? Probable solution, that means one probable tree, because you have to remember that salesperson has to visit all the cities. So salesperson, let's say the starting city is A, so that means salesperson will again come back to the city A. So he can visit from A to B, and then B to C, and then C to D. By this process, he will be visiting all the cities exactly once, and then he can again come back to city A. Similarly, salesperson also can visit city A to B, then B to D, D to C, and then finally C to A, if there is a connectivity is there. Okay, so this is a situation we have. So these are all the probable solutions that is possible is given. Now let us come back to the solution. So let's say this is the matrix given, weight matrix, and this is the corresponding graph where four cities are there. So how to get this problem solved by dynamic programming, that you have to see. So this is the probable tree that we have, solution tree. So city A to B, then B to C, C to D, and then D to A. So you can see in this path, A to B, B to C, C to D, and D to A. This path, in the last if node, that means when the city, when the salesperson is actually visiting to the starting city again, coming back to the starting city again. So D to A, so D to A, the distance is 9, so we'll write here 9. Okay, C to A, C to A distance is 4, we'll write here 4. Then D to A, D to A distance is 9, we'll write here 9. And then B to A, B to A, according to the weight matrix, distance is 7, we'll write 7. And then C to A, C to A distance is 4, we'll write here 4. And then B to A, B to A distance is 7, so we'll write here 7. Okay, so these are all the distances that we have calculated from the second last city to the starting city. Okay, now we can see that, so once salesperson is visiting from D to A, it is 9. So but then before that D, we have city C. C to D, how much the distance is? C to D. So first we have to see that C to D. What is the C to D? C to D is 1. Weight matrix value that is given, C to D is 1. So C to D is 1. Okay. So 1 plus this 9 is equal to 10. C to D, C to D, in the weight matrix it is given as 1, and salesperson already has figured out what is the distance between D to A, which is 9. Obviously, if he wants to visit C to D, 9 plus 1, which is equal to 10. Similarly, from D to C, C to A already he has figured out it is 4. But D to C, in the weight matrix, D to C is given as 2. 2 plus 4 equal to 6, which is equal to 2 plus 4 equal to 6. So D to C is 6. Similarly, B to D is 14, D to B is 11, and then B to C is 10, and C to B 10 again. Now you have to come to the second level, that is B to C. Salesperson can visit B to C, or salesperson also can visit B to D. So whichever is the minimum, salesperson will choose that. That is the dynamic programming catch here. Okay. So B2C, B2C, we can see that B2C is given as 6. Okay. And D2C already you have calculated, which is 10. So 6 plus 10, 16. This is 16. B2C. Whereas B2D, which is already we have calculated, D2C is 6 and B2D is given as 5. 6 plus 5 is 11. So out of 16 and 11, 11 is the minimum. So obviously, salesperson will choose B2D, which is 11. Similarly, for from C to B and C to D, whichever is the minimum, we have to choose that, and it is 12. Minimum value, calculated value is 12. Similarly, from D to B and D to C, whichever is the minimum, salesperson will choose that. In that case, also minimum value is 12. Now, once salesperson wants to visit A to B, A to B is already given 2. So 2 plus 11, 13. And A to C, because salesperson at this root node, salesperson has three choices: A to B, A to C, A to D. A to B is 2, 2 plus 11, 13. A to C is A to B, 2 plus 11, 13. A to C is 3 given in the weight matrix, 3 plus 12, which is equal to 15. And A to D is given as 4. So 4 plus 16, 4 plus 12, which is equal to 16. So out of this 15, 16 and 13, 13 is the minimum. So that means the optimal cost is 13 here. Okay, optimal cost is 13. So the visited nodes will be A, B, D, E, again A. So this creates a cycle. So that means salesperson has visited all the cities exactly one he visited, B exactly one he visited, D exactly one he visited, C exactly one, and then again comes back A, which is twice he is visiting. The total cost is 13. Okay. Now, as I said here, when salesperson visiting A and then after that B, he has two choice. One is B to C, B to D. So B to C, this is given 6, and C to D, this is 10. Just here we have calculated. So this one is minimum one. So he will choose this minimum path. Okay. So 6 plus 10, 16, 5 plus 6, 11. That already I explained, but again I have put it here. So like that, the minimum path salespersons will be choosing using dynamic programming. Now, what is the time complexity? We'll come back to it later on. But how to do the formulation? That means function. What is the function that is there for this solution? So using dynamic programming, let's say gi comma s is the function. So I is the starting vertex, and s is the set of vertices that salesperson is choosing, excluding the starting vertex. Okay. So GIS. So minimum path we have to choose minimum of I to J plus G of J, because already you have chosen J, so S minus J excluding J. So this is the you can call it the formulation or the function. So what is happening here? So I to S is the set of vertices, and I is the start vertex. So Wi comma J comma J, because you have chosen J already, so you have to exclude J. That CD cannot be chosen further. So S minus J, and then J belongs to S. So let's say initially starting vertex is A. We have chosen as A. So at the initial stage, we have A, B, C, D. A has three options: B, C, D. Okay. So how it will be expand this function? Already you have seen that, but in function point of view or the function formulation point of view, how dynamic programming will explore this. The minimum of A to B plus G of B and C comma D. Okay. So G of B comma C comma D. G of B comma, so this one G of A to B and then CD, what is the distance? So that we have written it here. This is what is the minimum of this, and then minimum of A to C if it goes from A to C. So this is this first function is for if it goes from A to B. Second function if it goes from A to C. So A to C W, A to C whatever the cost is, plus G of C D comma D. And then finally if it goes from A to D, then A to D W A to D plus G D B comma C. Okay. So this is how to calculate. Let's say we are taking the first one, this component, second part of the first function. What is the minimum value? The G B comma C comma D. This one. So this one, how to calculate G, B, comma, C, comma, D. So we have to first explore what is the distance between B to C plus G, C. Already we have taken C here, so C, comma, D. C, comma, D. This is the function of G. Now this again will be expanding. So C, G, C, comma, D. is nothing but W, that means distance between C comma D plus G D comma phi, because already you have chosen here C, so there is nothing left. So D comma phi. So this is nothing but this phi means that D, after D again it is visiting to A starting vertex. So this WC comma D in the weight matrix C comma D, it is given as 1. This is 1. And G D comma A, that means what is the distance between D to A? So D to A is 9. 1 plus 9 which is equal to 10. So this is 10. This part is 10. And W B comma C is already given. B comma C is already given 6. So 10 plus 6 which is equal to 16. So this is nothing but 16. That means these calculations already we have done here is 16. 16. Okay. Similarly, if you take the another one, B comma D, W B comma D plus G D comma C. So again this and this WB comma D plus G D comma C, which is nothing but WBD plus WD comma C plus G C phi. That means this is the last one. That means C to A. Again it is visiting. So it has visited C, and then after C it is visiting A. So this WB comma D is already given. B comma D is 5. This is 5. WD comma C is 2. This is 2. And G function G C comma A. This 5 means it is again visiting the starting vertex C to A, which is nothing but 4. C to A is 4. So this is like total is 5 plus 2 plus 4, which is nothing but 11. So out of this, so this 11 also you have to calculate here is 11. This side it is 11. This side it is 11. So what we have done, we have first calculated C to A. This is C to A, C to A, and then D to C, then D2C, D2C, this one also you have calculated, which is 6, D2C, D2C, which is equal to 2, D2C, and then B2D you have calculated, B2D, this B2D also you have to calculated is equal to 5. Total it is 11. The minimum of 16, and minimum of 11, which is equal to minimum is 11. So we have chosen here 11. We have chosen here 11. Chosen here 11. Similarly, from this route, we have chosen minimum is 12. From this route, it is 12. So out of this thing, only this one is minimum. Now, if you add, this is minimum. However, in the A to B and A to C and A to D, again A to B gives us the minimum, because A to B in the weight matrix, A to B is given as 2. So 11 plus 2, 13, which is the minimum cost. So this is called, this is how you should solve. And the final result is A, B, D, E again A. A, B, D, C again A, because the 13, cost is 13. So what is the time complexity of this algorithm? Time complexity is, time complexity of this algorithm is uh, we go of n square plus into 2 to the power n, which is exponential by nature, and space complexity of is we go of n 2 to the power n. So this time complexity and space complexity both are not good, but this is just to show that dynamic programming, how it can be solved. I hope you understood.